So, with the fundamental idea of spectrophotometry being that we're using light to make measurements, analytical measurements of molecules or atoms, we need to understand light. Light is a little bit of a wily thing. We often describe light in terms of as acting like a wave, so it has wave-like properties. And light is an electromagnetic wave, represented here by a figure from your textbook, where we have an electric field oscillating. So that's this this blue line that's going up and down. And perpendicular to it, in the z direction, we have a magnetic field that also oscillates at the same frequency. And this is a self-propagating wave. Has a particular wavelength that's indicated by the symbol lambda. Lambda represents the distance between the highest point of the wave to the highest point again, right? So peak to peak, or you can go from the bottom, trough to trough. But that's the wavelength. The other thing that's important is that if we consider this as a wave, so we have the wavelength, we also have a frequency, which is how many cycles do you have every second. If we multiply those together, that gives us the speed of the wave, which we call c, and this is the speed of light, which is a constant, a fundamental constant of nature, and nothing can go faster than the speed of light. So frequency, so nu here is frequency, and again, that's how many cycles of the wave past a given point per second. So this is in units of hertz, which is the same as 1/second, or cycles per second. And then we have this is the wavelength, which again is defined as the distance between one peak to the next peak. For light, this is so this is going to be a distance. This is often written in nanometers, but fundamentally it can be written in any distance unit that works. But for visible light, nanometers is the most common distance scale that makes the most sense. But you can have wavelengths ranging from meters for radio waves all the way up to smaller than nanometers when you get to X-rays and UV light. Anyway, so those are some of the properties that we need to be thinking about. The speed of light, c, you can look this up, and this is defined specifically, it has a lot more digits than this, but 2.998 times 10 to the 8th meters per second. And this is the constant that allows us to convert from the frequency to the wavelength and vice versa. Now, so that's the wave-like properties of light. We can describe it as this oscillating electromagnetic field with the speed of light fixed, and we have the wave properties of frequency and wavelength that can describe the light. But we also can describe light as a particle. And we use both descriptions depending on what is more convenient. Light behaves in both ways. It behaves as a wave and a particle. And so we call a particle of light a photon. I believe that term was coined by Einstein. So we call a particle of light a photon, and that is like a packet of energy. And this particle-like nature is sort of summarized in this equation here, E equals h nu. The amount of energy in a given photon is given by a constant called Planck's constant, times the frequency of that light. So this relates our wave picture and our particle picture. So this is the same frequency that's in the other equation. So the energy light comes in little packets of energy, and you can't have any less energy than that. And the amount of energy that's part of that is given by this equation, E equals h nu. H is Planck's constant, which is equal to 6.626 times 10 to the minus 34. So it's a very small number, joules times seconds. Okay. So just looking at my notes here. So the energy of the light is directly related to its frequency, and it's inversely related to the wavelength. So we can capture that in this equation here that sort of combines these other two equations. E equals hc over lambda. So that combines these other two equations. If we substitute c over lambda for nu, that gives us this equation. And we often write 1 over lambda, we give it its own symbol, nu with a tilde over the top of it, and we call this the wave number of light. Us spectroscopists really like to use this unit, particularly inverse centimeters, because it is directly proportional to the energy of the light, and sometimes it's a lot more convenient to use than wavelength directly, though it depends on which who you're talking to. As an infrared spectroscopist, we always use wave numbers. Visible light spectroscopists like to switch back and forth between nanometers and wave numbers, so you kind of get both. But this is, again, a common use among spectroscopists, and it's what's nice is that, as we can see in this equation here, the energy and the wave number are directly related to each other. They're directly proportional, whereas energy and wavelength are inversely proportional. And in theory, there is no limit to the values of the wave number and or wavelength or frequency, right? These values can take a lot of different possibilities. And in the next video, we'll look at the different regions of the electromagnetic spectrum and what sort of properties of matter they address.